So in this talk, I would like to share my work on artistic portrait style transfer. I will first introduce the background, then I will introduce our proposed dual style GAN and V25 in detail. Finally, I will conclude my talk. The first is the background. So image style transfer is a technique that enhances the artistic style of an image. It can enrich the image content and deliver emotions. Because of its entertainment function, it is widely shared on social media. At the same time, because of its certain artistic nature, it is widely used in graphic design. Exemplar-based image style transfer takes an content image and an example style image as input. The stylized image should match the styles of the style image, such as the color and the textures, while preserving the structures of the content image. Exemplar-based style transfer is flexible since users can select the style image to specify their favorite styles. In this work, we explore exemplar-based style transfer for face images. Here are two examples. In the first example, we use paintings as the style image. And in the second column, second row, we use the artistic portrait as the style image. We can see that compared to arbitrary paintings as the style image, using artistic portrait as the style image will generate more meaningful results. Therefore, we focus on transferring the style of an exemplar artistic portrait onto a target real face. In this task, in addition to the colors, textures, and simple patterns, the method should also pay attention to the face shapes for precise passage. For example, we need to exaggerate the nose of Jackie Chan to render a caricature portrait. Here are more examples. You can see besides the color, we also need to mimic the change the eyes shapes to better mimic the style of an artist. In previous studies, portrait style transfer can be realized by an image-to-image translation framework to learn a bidirectional mapping between the real faces and the artistic portrait faces. However, learning from the scratch on this complex bidirectional translations makes this framework limited to low resolution images and requires.
Sorry to interrupt here. So perhaps you want to move your microphone a bit further from your mouth.
Okay.
Yeah, because you see that the air just
okay.
a bit noisy. So yeah.
And yeah. So this voice is all right.
Yes, we can hear your voice very clearly. So
the image-to-image translation usually is limited to low-resolution images and requires long training time. Meanwhile, portrait style transfer can be more efficiently realized by transfer learning on StyleGAN, which is called Tonify. StyleGAN is a powerful multi-layer generative model. It can map random latent code W to realistic faces. Each layer of StyleGAN characterizes different face styles. For example, low-resolution shallow layers captures facial pose and structures. High-resolution deep layers captures color and textures. Therefore, we can fuse the styles by mixing features from different layers. As shown in the right, this row provides the deep layer features, and this column provides the shallow layer features. So if we fuse the deep features with shallow features, then we can see that we can combine the colors and textures of these faces with the structures of these faces. If we gradually mix more deep layer features from the bottom row, the result will gradually have more structures of the structure of the face will look more like this, the column. So this good property makes StyleGAN a powerful model for face stylization. In Tonify, by fine-tuning a pre-trained StyleGAN-based model on the cartoon dataset, the two models can generate a realistic, photorealistic face and is stylize the content part from the 7 latent code. Style can be further controlled by blending the two models. For example, we can use the deep layers of the base model and the shallow layers of the transferred model, so that the results have realistic colors and cartoon-like face shapes. The fine-tuning only requires a small data set and a few iterations. However, although very efficient and supporting high-resolution images, Tonify learns an overall translation of the distribution, incapable of performing exemplar-based style transfer. As can be seen in this example, the dataset, the styles in the dataset are very diverse. However, the model only learns a relatively realistic style one. Considering the advantages and disadvantages of previous studies, our goal is to build a user-friendly automatic passage framework to allow the users to collect a few portrait images of their favorite artworks and train a model to passage. We further would like to extend the model to videos. This requires the model to handle unaligned faces. To this end, we introduced a novel dual StyleGAN for exemplar-based style transfer, requiring only a few hundred style examples. It offers high quality and high resolution passages and provides flexible and diverse control over both color styles and complicated shape styles. We further extend dual StyleGAN to a video style transfer framework named Tonify. It inherits the good property of dual StyleGAN on style controllable high resolution face style transfer. Besides, it can be trained without real data and it can handle unaligned dynamic faces in videos. Now let's look into dual StyleGAN. Dual StyleGAN is based on StyleGAN, but it follows the standard exemplar-based paradigm. The standard exemplar-based paradigm is shown here. Usually we have a content encoder to extract the content feature and a style encoder to extract the style feature. Then we fuse the content feature and the style feature and use a decoder to map the fused feature to the output stylized image. In dual StyleGAN, StyleGAN serves as the content encoder and the decoder, which is fixed during training. We can see this part, in the left part, the StyleGAN encoder serves as the content encoder to extract the content features. Here, StyleGAN encoder is a pre-trained PSP network to map real faces to latent codes of StyleGAN. Meanwhile, the generator network serves as the decoder to generate the final outputs based on the content features and the style features. We add a new style path to extract the style features from the style image and fuse them with the content features in the StyleGAN. Now we call the content path as the intrinsic style path for face pose and identity, and the style path as the extrinsic style path for cartoon styles. We would like the fusion of the features from the two paths to simulate the transfer learning behavior on the StyleGAN itself, just as in Tonify. But how to design this extrinsic style path? Our design follows two principles of hierarchical and residual. First, the extrinsic style path should follow the StyleGAN's 18 layers, while low resolution layers depicts the shapes, styles, and the high resolution layers depicts the color and texture styles. Second, the fusion of style features and the content features should be in a residual way. Recent studies here find that in tonifying, the convolutional features of the base model and the transferred model has high correlations, so as their residual features. So we can predict the residual features from the base model and add them to the original features to obtain the transferred features. In this way, the transfer learning behavior is simulated with the base model fixed. Based on these two principles, we have the extrinsic style path as shown above. Specifically, we use a StyleGAN encoder to extract 18 style codes from a style image for the fusion in 18 layers. The first 7 layers transfer structure styles, while the rest block is used to predict the residual features. The rest block is further conditioned by the style codes using ADA-IN. The last 11 layers transfer color and texture styles, while the original ADA-IN based modulation and demodulation in StyleGAN is used for color adjustment. In addition, we add style degree weights W in each year, here, and here, so that we can control how many extrinsic styles are fused with the content features. For example, if W1 equals to 0, then no structure styles are applied to the first layer. Meanwhile, if W equals to 0 in the last 11 layers, it means these blocks are blocked. Then it means that the original color from the intrinsic style path will be preserved. With such design, we hierarchically model the styles for flexible manipulation. And with the original StyleGAN fixed to provide good features, we can preserve better structures and alleviate model collapse. However, adding a new path to the StyleGAN changes its generative space. For example, the original space has this space, but we add a new path, then the result will become messy. So we cannot directly fine-tune dual StyleGAN. To solve this problem, we propose a progressive fine-tuning scheme. It has 3 stages. In the first stage, we initialize the extrinsic style path so that it does not perform any structure adjustment, but only acts as the style swapping of StyleGAN in high resolution layers. This means we only perform color transfer on the real phase domain. We can see that we set the convolutional weights in modulative rest blocks close to 0, so the residual feature will be very close to 0. So we do not apply any structure adjustment. And here we just set this matrix, set this an identity matrix, so the input will directly be forwarded to the output. So here the model will use the original phase structures with the color styles of the style image. Then in stage 2, we train dual StyleGAN for structure transfer on real phase domains. We use style swapping in the low resolution layers to generate the fused phases, serving as ground truth pairs to train the network. So for example, in this example, we use the previously introduced style swapping to generate the to fuse these 2 phases to generate a fused phase. And then with this image as the style image and this image as the content image, we would like the model to produce an image to approach the ground truth fused image as here. So after this stage, our model learns to enlarge the eyes of this woman, but still produces realistic faces. Finally, stage 3 train dual StyleGAN for style transfer on the artistic portrait. We reversely perform tonifying here to destylize the cartoon face to generate the pale data for training. For example, for this style image in the training sets, we first apply the stylization to obtain this one. So with this as the content image, as the style image, and this image as the style image, content image, we will like the dual StyleGAN to produce the image to approach the ground truth cartoon image. After this stage, it can be seen that our model successfully transformed a real face into a cartoon face. With the paired data as anchor points, the model will learn individual styles of each example style image rather than an overall style of the entire target domain. We train and test the dual StyleGAN and cartoon, caricature, anime, and our collected 4 styles from internet. We only need about hundreds of images for training, and the training time takes about several hours. So let's see some experimental results. We can see the collection-based style transfer method, such as tonify, can only render a general cartoon style. Compared with other exemplar-based style transfer method, our method can best simulate the example styles in both color and face shapes. Here is more challenging caricature styles. We can see most method fails to transfer the exaggerated face shapes. Our method can generate the best exaggerated shapes as the exemplar styles. On anime styles, due to the imbalanced data sets, that is, the source domain has thousands of images, while the target anime domain only has hundreds of images. Some image-to-image translation method only just memorize the small data set. Here are more visual results. On the cartoon style, our method precisely passages the style of each example images, such as the soft lines of the Snow White. The next is the caricature style. Our method successfully exaggerates or shrinks the facial features to increase the artistry. The next is more abstract anime style. Here we show our results on animated faces. The results are smooth in motion. Besides, this is the caricature styles. And the anime style. So dual StyleGAN can also support generating random artistic portraits from random latent code. Here are our randomly generated images. Dual StyleGAN supports flexible style control for color preservation. For color preservation, we just replace the extrinsic color code with the intrinsic one, or just remove the extrinsic parts in the last 11 layers. Here are our style transfer result with color preservation. In addition, we can adjust the style degree weight W to make a minor style transfer to preserve more original face features. We can do style mixing in both intrinsic style paths and the extrinsic style paths to fuse different contents and different styles. In 3 distinctive styles of Pixar, Comic, and Slam Dunk, our method also achieves good performance. Although good results are achieved, dual StyleGAN requires the input phase to be aligned and cropped. This is called the fixed crop limitation of StyleGAN. This limitation is acceptable for a single image, but for videos, it will be unnatural if the phase is always fixed in the center of the canvas. Next, let's look into how we solve this limitation with V25. Here is an overview performance of V25. So let's first recapitulate the two deep learning framework for face tonification. So one popular framework is image-to-image translation. It learns to map the input face to a cartoon face through a fully convolutional encoder-generator architecture, which has less restrictions on the image resolution and the face positions, which is good for video style transfer. But training from the scratch, it suffers limited image resolution and many artifacts. Another popular framework is based on StyleGAN for high resolution and style controllable tonification. However, StyleGAN can only produce images with aligned faces and on the fixed resolution. This is because StyleGAN's first layer is a constant feature map with fixed resolution. In V25, our key idea is to remove this fixed input feature and add an encoder for providing features of variable resolution. Thus, we can build a fully convolutional encoder-generator architecture to stylize the full image based on the style conditions and the multi-scale content conditions. By considering the temporal consistency, we can even tonify videos. Thus, we call this framework V25. As a summary, V25 can turn videos into different styles like caricature and cartoon with a high resolution. It distills the StyleGAN model and inherits its flexible style control. We can control the style types, the color, and the intensity of the style. V25 is data-friendly. It can be trained on paired data generated by the StyleGAN model. Thus, we do not need to collect the real training data. V25 builds upon StyleGAN-based backbones, tonify, and dual StyleGAN, and extend the tonify and dual StyleGAN to video tonification. Let's first take a look at the backbones. Previously, we have introduced the tonify. Given a pre-trained StyleGAN-based model for real face generation, tonify fine-tunes it on the cartoon dataset. Then the two models can generate real faces and their stylized versions from the same latent code. And in the last part, we have introduced the dual StyleGAN in detail. Briefly, dual StyleGAN introduces an external style path to the StyleGAN-based model. The style of the output is conditioned by the external style code. Next, let's look into how we extend the tonify and the dual StyleGAN to videos. We start from tonify as backbones. In our task, our input is a real face image. Tonify uses a style encoder, the PSP encoder, to extract its style code as the style condition. As previously mentioned, to overcome the fixed crop limitation, we will remove the first few layers of tonify. The remaining part is used as our generator G. Then we add a trainable encoder to extract the content features of the input image. To preserve the details of the input image, we sent the encoder features forward to the generator with skip connections. So we have multi-scale content features as content condition. Finally, we fuse the encoder features and the generator features in a trainable fusion block by concatenation and convolution. Now we have extended the architecture of tonifying to V-tonify. Next, we would like to train V-tonify with the paired data XY generated by tonify. We generate real faces from random latent code with StyleGAN and stylize them with tonify. Finally, to make V-tonify works for unaligned faces, we further apply random geometry transformation to these images. Although data generated by tonify is of fixed size, V-tonify is fully convolutional, can be trained on fixed resolution, but tested on variable resolutions. Given X and Y, during training, we would like V-tonify to map X to Y. This leads to a reconstruction loss. We add a discriminator to compute the adversarial loss, which improves the realism of the output. For temporal consistency, we simulate the camera motion. The parallel movement of the camera with a limited field of view captures 2 subframes from a single frame. If the camera is sufficiently far away from the face to ignore the 3D effects, the overlapped region of these 2 subframes should be the same. Correspondingly, we would like the overlapped region of their stylized results to be the same. Here, it leads to our flicker suppression loss. These 3 losses is our final training objectives. Now we have introduced how we extend the tonify to videos. The way of extending dual StyleGAN to videos is quite similar. With dual StyleGAN as the backbone, we have the pink extrinsic style path to accept the style condition from the style image. We just make the extrinsic style path to interact with the content features of the rest blocks in the encoder. Besides, dual StyleGAN has 1 more parameter style degree as the condition. Correspondingly, we update the fusion block with a new mask. The mask is conditioned by the style degree. Intuitively, a small style degree leads to a large mask to pass more original content information to the generator. A large style degree leads to a sparser mask so that we will use less information from the input frame to give room for greater cartoon style effects. As for training, we use dual StyleGAN to generate the paired data with the style condition W prime and the style degree DS. We generate real faces from random latent code with the StyleGAN. Generate the style condition W prime to stylize the face with dual StyleGAN under the style degree DS, and apply random geometry transformation. To make the network learn color transfer, we further apply color jittering to the real faces. As for the training objectives, in addition to the aforementioned reconstruction loss, adversarial loss, and the flicker suppression loss, we add a mask loss to penalize large masks so that only valid content information is used. That's all of our framework details. Let's see some experimental results. Here is an overview of our tonification results. We tonify inherits the ability of flexible style control from dual StyleGAN. Let's take a look at this example. This is the default style setting. Besides the default style setting, we can adjust the style degree to make the style stronger or weaker. We can select different cartoon styles based on different exemplar style images. For example, the big eyes or the masculine style. The cartoon styles and the style degree can be adjusted simultaneously. We can also transfer the colors. Besides the cartoon styles, here are 3 other impressive styles of arcing, pixel, and comic. Next, we compare our method with our backbones 25 and dual StyleGAN and the pixel-to-pixel HD. It can be seen that the results of our backbones have limited views, and the pixel-to-pixel has many artifacts. All the compared methods suffer from annoying flickers. By comparison, our method generates smooth and high-quality results. Here are more examples. We further compare with 2 image animation methods. The FOM and the first order motion and StyleGAN are based on dense motions, which are hard to predict for complex things, leading to blurry results. By comparison, our method better preserves these structures and details. Here we show the effects of our flicker suppression loss. It can eliminate the flickers in the hair regions. We investigated the multi-scale content features in preserving the details. With only a single layer content feature, the hair and the patterns in the clothes become very blurry. By using our multi-scale content features, these important details, which are hard to encode and reconstruct within dual StyleGAN, are effectively synthesized. However, we should avoid overusing these features. Here is an example of the ghosting artifacts at the edge of the clothes. To solve this problem, we introduce the mask and the mask loss. We compare the result with and without the mask loss, and show the estimated masks in our 4 fusion modules in the generator. The model without the mask loss overused the content feature, leading to the ghosting artifacts. By comparison, the mask loss imposes the sparsity of the mask, enforcing the model to select only the valid information, like the clothes, the background, the hair, to generate the more plausible results, avoiding the ghosting artifacts. You can see that the edges of the clothes has low values in the mask. Here are more results of V25. So these are the cartoon cells. This is the comic cells. And the pixel cells. To conclude, we propose a data-friendly exemplar-based portrait cell transfer framework dual StyleGAN, where we design an extrinsic cell path for hierarchical cell manipulation and a corresponding robust progressive fine-tuning scheme. Based on dual StyleGAN, we further propose V25 for cell-controllable high-resolution video tonification. It combines dual StyleGAN and image-to-image translation to enhance the advantages of both models. That is the flexible stand control and the ability to handle unaligned faces in various resolutions. So that's all of my talks. Thank you. Here we provide the web demo of dual StyleGAN and V25. Have fun with it.